Hello and welcome to Science Talk. I am your host, Jim Massa. In another video exclusive for my Patreon subscribers, I want to discuss with you an alarming development concerning our oceans. The ocean is suffocating and it's our fault. So this comes from an abstract. And this is an article that appears in the journal Science with the lead study, and author is Denise Breitberg. She is a marine ecologist with the Smithsonian Environmental Research Center. So, reading from the abstract. When dissolved oxygen in water is depleted, fish pay the price. Pollution can rob marine ecosystems of their oxygen. It was noted on March 6th, year 2000, thousands of dead fish surfaced in the Rodrigo de Freitas Lagoon in Rio de Janeiro, Brazil. These fish were suffocated after pollution flooded the waters. Low oxygen zones are spreading around the globe. Coastal regions where there is upwelling are productive areas. Lower DO levels, DO is dissolved oxygen, lower DO levels bode poorly for organisms. This has serious implications for humans who rely on food from the sea, especially fish. Okay, so let's break this down. Dissolved oxygen. That's oxygen that's actually in solution in the water. Okay, it's not where, I take a hose that's pumping out oxygen and I stick it in the water and you see the bubbles. No, it's the oxygen that actually dissolves in the water. Now, oxygen, the solubility of oxygen increases with a decrease in water temperature. So, you take a fish like a trout needs a high oxygen level in the water to survive. So where are you going to find a trout? In cold water streams. Compare that to, say, a bass or a catfish that can tolerate lower oxygen level and will be found in warmer waters. So that's one thing to keep in mind. The solubility of oxygen increases with a decrease in temperature, decreases with an increase in temperature. Inversely related. There's another concept called biological oxygen demand. And this is basically the oxygen requirements of organisms. Generally speaking, if the BOD, as it's called, increases, that means what? The organism is demanding more oxygen, using up more oxygen. The dissolved oxygen content or concentration decreases. This is a problem with eutrophication, which is a form of pollution. The additional fertilizer that ran off from farms and goes into the water system. And what happens? You have all this nutrient that's pumped into the system and the algae just go nuts. Hey, we've got all this stuff here and boom, and they bloom. Well, plants do not just use CO2. Plants also have to respire. They also use oxygen. So you have all this bloom here, the BOD is increasing. The algae, when it does its respiration, will use the oxygen. The oxygen level goes down. Not enough oxygen for the fish. Fish die. That's basically the crux of this. Increased pollution, the BOD increases, the DO decreases. You have mass fish kill. Okay. So, ocean dead zone. A little more background on this. Ocean dead zones. This is regions of the sea where oxygen is severely or entirely depleted. Most forms of life obviously cannot survive. Such regions are becoming more and more numerous and more widespread. Part of this is not only reduce the pollution, but we need to reverse global warming effects. So, rising global temperatures and influxes of nutrient pollution, that's the excess nutrient input, that's called eutrophication, are basically squeezing out oxygen level. It's removing oxygen levels in the open ocean and coastal areas, threatening communities of sea life around the world. And less oxygen in the ocean does not only spell trouble for marine plants and animals, it carries serious repercussions for life on land as well. Okay. As I mentioned earlier, oxygen dissolves in the water. Liquid water must also contain dissolved oxygen, because what the fish does is the gills removes the oxygen that's in solution. If I took that air hose that's blowing out oxygen and I shove it in the gill of the fish, I'm not doing it any good. It won't be able to use that oxygen. The oxygen's in solution, it diffuses across the gill membranes. Then it's picked up by the blood vessels and distributed around the body and so on. Fish have a two-chambered heart typically. Okay. Since the growth of industrial and agricultural activity has disrupted oceans' chemical balance, many regions worldwide are becoming, there's more and more pollutants, more and more nutrients that are starving the water of oxygen. Rising global temperatures hampers oxygen solubility, right? You just heard me say that the solubility of oxygen will decrease with an increase in water temperature. So we have a two-pronged nastiness going on here. We have BOD increasing, resulting in a decrease in DO, and in addition, increasing temperatures, reducing the solubility of oxygen. This is leading to dead zones. This is leading to not enough oxygen for the fish, and the fish are dying off. Not good. And if you have, especially the surface waters are really warming up. If you increase the temperature of the surface water, you're decreasing the mixing of the air of the oxygen at the air-water interface, and to couple that with the increased temperature, making solubility less likely, decrease in solubility, that also has the further effect of having less oxygen available to deeper depths in the ocean. There's less oxygen that can be mixed down to deeper depths. This is also causing increased stress on many marine life due to warmer waters. But also, we have yet another problem. We also have CO2 mixing at the air-water interface. What does water plus CO2 equal? Carbonic acid. Yes, it's a weak acid, but it's still an acid. So we now see acidification of the ocean. The bleaching of corals, for example. That's the result of the polyps that live within the calyces of the coral dying because the symbiotic algae can't handle the increased acidity. The symbiotic algae is called zooxanthellae. So, when those polyps die, you're left with the calcium carbonate skeleton, hence the coral bleaching. All that nice little coloring that you see there are the polyps from the organisms that are extended out into the water, filter feeding. The other problem is that as you acidify the ocean, you dissolve calcium carbonate. There are many organisms that have a calcium carbonate shell. You start dissolving it, or you're making the shell thinner and so on, the organisms are not going to survive as likely. So, yes, we started this segment out talking about specific situation in Rio de Janeiro, but this is a global phenomenon going on. Team of scientists from you're going to love the acronym on this one, from the Global Ocean Oxygen Network, or GOON, Who says scientists don't have sense of humor? Anyway, but it's a group formed by the United Nations Intergovernmental Oceanographic Commission, and they found that the toll on Earth's ocean has been significant. I've already kind of briefly outlined to you the problem with the increasing temperature, reducing the solubility of oxygen, but also we now have CO2 mixing in with the water, creating carbonic acid, which is creating an acidifying situation in the ocean. This is what they have found. Over the past 50 years, the ocean suffered a loss of about 85 billion tons, 77 billion metric tons, of oxygen, affecting an accumulated area approximately the size of the European Union. That is not insignificant. Globally, the amount of zero oxygen ocean water has quadrupled. Zero oxygen is what it sounds like. There is no oxygen in the water. It's what we call hypoxic. While the area occupied by low oxygen zones has increased 10 times. In coastal areas and seas that are semi-enclosed, once low oxygen conditions are established, they can persist for thousands of years. That is because if they are isolated, there's not much communications for any influx of material to, quote unquote, rejuvenate, if you will, the area or infuse oxygen into the area. If we lost 4.5 million square kilometers of productive area on land, everyone would be appalled. But that's exactly what's happening in the ocean. That's what Professor Brightberg said. What happens beneath the surface of the ocean is out of sight and easy to not notice or ignore. As oxygen, she goes on to say, as oxygen levels in water drop, the behavior and growth of fish and other ocean organisms is affected. A lack of oxygen can make them more susceptible to disease or make it more difficult to reproduce. Extreme cases, they suffocate. While certain types of microorganisms may thrive under low oxygen conditions, pick your bacteria, right? Most larger forms of sea life either die or abandon oxygen-starved waters. What happens? They go to nearby ecosystems where they put a stress, a strain on that particular web, and that could disturb the balance that goes on over there. It could disturb the food web, it could increase the vulnerability to predation, etc. That's what these Dr. Brightberg and her colleagues describe. So, how can we restore oxygen? Some cases, evidence shows that the damage can be reversed, and areas where nutrients and sewage had sucked oxygen from the water may yet recover once the flow of contaminants is removed. So says Dr. Brightberg. Because, as I explained earlier, excess nutrients, the producers will use up the available oxygen, which then deprives the heterotrophs. Okay, in Maryland, the Chesapeake Bay, long known for dead zones, that seasonally covered about 30% of its area, nitrogen pollution levels have decreased by 24%, which is a result of improved farming practices and sewage management, and better air quality as well under the Clean Air Act. And basically this is allowing oxygen levels to return. When it comes to oxygen loss in the open ocean, this is completely new, Dr. Brightberg explained. We don't know how long it will take for the ocean to respond. Now, I could get into, and I will briefly here, about the middle of the ocean, oceanic gyres. Before I do that, let's just close off with what the study is telling us. Addressing the global issue will require worldwide cooperation and initiatives to mitigate fossil fuel emissions and curb nutrient pollution. establish more protected areas in the ocean, support policies that preserve threatened, vulnerable marine life, help struggling ecosystems recover. Dr. Brightberg concludes, slowing and ultimately halting the decline of oxygen in the open ocean and oxygen decline in coastal waters that is due to climate change will take a global effort, not only climate change, but nutrient pollution, but needs to be done not only to improve oxygen in the ocean, but to avoid the worst that devastation global warming can cause. Because if the fish start dying, and a lot of people depend on fish for their food, you don't need to be a rocket scientist to understand the serious implications of that. Now, the open ocean. The open ocean, for starters, is considered to be a biological desert. Not much productivity happens in the open ocean. Let's, for example, let's consider the North Atlantic. The North Atlantic, we have a nice gyre. You have the Gulf Stream that goes up the eastern seaboard. It swings over towards Greenland and Iceland and Norway and Scandinavia and so on. It gives off its heat, the water sinks. That's another video. I'll talk about the conveyor belt in another video. But there's also a surface return current that is, whereas the Gulf Stream is narrow and strong flowing, what we call western intensification of gyres, on the eastern side, like off Africa, is slow moving and the current is wide and it's a surface flow. And it comes back here. But in the open ocean, with the gyre that's flowing in a clockwise manner in the northern hemisphere, when we consider Coriolis, the Coriolis effect is a apparent deflection. In northern hemisphere is to the right, southern hemisphere being to the left. So as the water's moving, it's deflecting to the right, and it's doing what? It's going to build up in the middle. Well, we have a concept called continuity of volume. So if water's piling up here, it's got to go somewhere, it goes down. We call that a downwelling. So in the center of gyres typically in the ocean, the middle will be, especially if it's a clockwise in the northern hemisphere, a clockwise rotating gyre, you have a downwelling in the middle. Well, downwellings are not very productive area because the nutrients are being removed and nothing's being made available. Not much happens in the middle of the oceans in terms of biological productivity. Contrast that with the counterclockwise rotating gyre in the Gulf of Alaska. Well, if it's counterclockwise rotation, you're going to create a void in the middle, and you have to fill that void in with water from below, upwelling. And when you have upwelling, you bring up nutrients. It's no accident that the Gulf of Alaska is a highly productive region, because we have an upwelling bringing in nutrients. Then you get sunshine creating what's called a pycnocline, but you get a stratification of the water where the phytoplankton are trapped in the photic zone, where the light level reaches. All the nutrients are in place, they go to town. And then you have the copepods and the zooplankton munching away, and then small fish munch away on the zooplankton, etc. Coastal regions are regions of upwelling. Let's say you have a current that is flowing along a coast. Well, you have Coriolis pushing that away from the current, away from the coast, excuse me. And there's also a thing called an Ekman spiral. I don't want to get into the intense physics and mathematics of it, but when we have the Coriolis and a rotation, we create an Ekman spiral, which if you integrate over the water column, I know I said I try to avoid the mathematics, but can't help myself. If you integrate it over the water column, you have what's called an mass Ekman transport. The result is that in the northern hemisphere is to the right, just like with Coriolis. Well, that creates a void along the coast. Upwelling. So when you have coastal upwelling, guess what? It does the same thing, brings nutrients in. So, but now if you have lower oxygen level and coupled with nutrient pollution coming in, coupled with upwelled nutrients, you're going to create a situation of increased BOD and decreased DO. And the organisms that we like to harvest will be detrimentally affected. Not only just fish, but it could be mollusks, other crustaceans and so forth. So this is a big problem. And considering that the oceans cover about 70% of the Earth's planet, of which, of that 70%, probably a good 15 to 20% is productive, and the productive areas are close to the coastlines, and almost basically half of the world's population lives within 50 to 100 miles of the coastline, you can see why this is a problem. So we have a twofold, really bad situation going on. Increased surface water temperature, decreases solubility of oxygen, but you also, because of the burning of the fossil fuels, you're mixing in CO2, making carbonic acid, along with nutrient input from land, like agricultural practices, and the combination is not good. It's not good for fish, it's not good for the ecosystem. But anyway, this is important to be aware of. Steps are needed to be taken to mitigate and reverse what's going on, because if we can't get enough food from the ocean or anywhere, we're going to have mass starvation, and millions of people are going to die. So this does have grave consequences for humans. I hope you found this video informative, but once again, human activity has side effects that are not necessarily good, and this is definitely one of those situations. Again, this is an exclusive video for my Patreon subscribers. I thank you for your time.